Okay, so for this problem, we're going to be doing 16 on the EE301 12-week review packet. So this problem concerns power, complex power, and parent power, also reactive power. So the first thing you need to remember when you're doing these powers is you need to remember how they're labeled. So real power is labeled in watts or kilowatts. Reactive power is labeled in volt amps reactive and can be either positive or negative. Complex power is in volt amps, and it is labeled with a magnitude called apparent power and an angle. It is a phasor. So let's get started with the problem. Draw a power triangle for the load and label the apparent, real, and reactive power. All right, so our first step is to take a look at what we have. Here we have watts, which means this is our real power. Here we have volt amps reactive, which gives us our reactive power. So the first thing we want to notice is that this is attached to an inductive load, which means this is a positive 400. Okay, inductors have positive reactive power, capacitors have negative reactive power. So last, what we'll need to do is we'll need to solve for our complex power. Our complex power is just going to be equal to P plus JQ. It's as simple as that. So that would mean 160 plus J 400. And it'll be more useful for us to put that in polar. So what we'll do is we'll just pop that into the calculator and put it in polar mode. That's 160 plus J 400. And that'll give us 430.81 at an angle of 68.2 degrees. And that is in volt amps. So when we're drawing our power triangle, what we do is we first just draw our P value. So that's 160 watts. And then we'll draw our Q value. So we know Q is positive in this case, so just go straight up. If you had a inductor, it would go down. So that's 400, or sorry, if you had a capacitor, it would go down because it would be negative. So that's 400 volt amps reactive. And lastly, we'll draw our S value, which is the magnitude apparent power, 430.81. And then we have our angle here. Our angle is that angle attached to the complex power, which is 68.2 degrees. And that is our power triangle. The next step is to find the source current. So when you look at your equation sheet, you'll notice a couple equations for complex power. We have one that says complex power is equal to voltage times current, complex conjugate. We have one that says it's equal to the magnitude of the current squared times the impedance. And we have one that says it's equal to the magnitude of the voltage squared over the complex conjugate of the impedance. We're going to use this equation because we were given the voltage and we have complex power already. So what we'll do is we'll just rearrange this equation over here to say that the complex conjugate of the current, the complex conjugate is that star, and that means that it's equal to complex power over the voltage. So that would mean 430.81 at an angle of 68.7 over 220 at an angle of 40. And that's given right here. Plug that in and we get, put that in, and we'll get roughly 1.96 at an angle of 28 degrees. And the last thing to do is to say, oh, well, if that's the complex conjugate, all I have to do to turn it into the actual current is flip the sign on the angle. So 1.68 at an angle of negative 28. And that is our answer. Lastly, we need to determine, we need to do what we call a power factor correct. Now, I'll read the problem. Typically, we reduce the source current. We can accomplish this by adding a capacitor in parallel to the load. The capacitor value is C, and it's determined by choosing a reactive power that will equal the inductive power. Find the capacitor component that will accomplish this. All right, so what do they mean by that? That means we have to find a capacitor that will cancel out our reactive power and turn reactive power total of the circuit to 0. So what we'll do is we'll say QL is equal to, what was that again? It was equal to 400. And that's going to be equal to the value of the capacitor we're going to add. Remember, we're adding the capacitor in right here in parallel with the load. So that means that we'll have to find the values that are relevant to that capacitor. So what are we trying to find? We're trying to find C. We have currently QC. We also have the voltage, right? Because the capacitor is in parallel with the source, which means its voltage is just the source voltage. So if we have Q and we have V, we can use the equation QC equals V squared over XC. That's on your equation sheet on the AC side. When we rearrange that, we'll solve for the reactance X of the capacitor, which is Q of the capacitor. Oops, my apologies. The voltage of the capacitor squared over Q of the capacitor, the reactive power. And that's going to be 220. Remember, this is just the magnitude. Squared over 400, which is going to give us 121. And that is in ohms. Next, we'll take XC and we'll rearrange it to solve for the capacitance. So that's capacitance equals 1 over omega times C, or XC. Remember, omega is 2 pi times the frequency. And if you look above, we were told that omega equals 500. So that's 1 over 500 times 121, which gives us a capacitor value of around 16.53 microfarads, farads being the unit for capacitor. So that is problem 16, parts A, B, and C.